Okay, let's continue the examples of a graph of a rational function. Uh, in this example, we have this rational function. R of x is equal to 2x squared minus 5x plus 2 over x squared minus 4. Okay. Step 1. We need to find the domain. Factor it. So for the numerator, it's 2, 1, negative 2, negative 1. 2 times 1 is 2. Negative 1 times negative 2 is 2. And then 2 times negative 2 is negative 4. 1 times negative 1 is negative 1. So sum is negative 5. It's exactly here. So you put x. So the numerator is 2x minus 1 times x minus 2 over denominator x squared minus a squared is equal to x minus a times x plus a. So x minus 2, x plus 2. And to find the domain, you only check the denominator. So the domain is the set of all real numbers except x equal to 2 or x is equal to negative 2, except those 2 points. Okay. But for this problem, you see here there's a common factor x minus 2 from top and bottom. So the lowest term is 2x minus 1 over x plus 2 is in lowest terms. But still, x cannot be equal to 2. And x is not equal to 2, x is not equal to negative 2. This is not all, this is end. Okay, so that's the domain and the lowest term. And step 3, let's look for the y-intercept, x-intercept. So the y-intercept you evaluate at 0. So r of 0. R of 0, you check the first one. This is 0, this is 0, it's 2. This is 0 minus 4, so it's 2 over negative 4. It's negative 1/2. So y of 0 is negative 1/2. And x-intercept, you need to look at the lowest term. The lowest term, you set 2x minus 1 over x plus 2 equal to 0. Now 2x minus 1 is 0. X is 1/2. So the unique x-intercept. Here x equal to 2. It is not x-intercept because it's not in the domain. Okay? And once you have x-intercept, you're going to study the behavior of the function closer to it. So near x equal to 1/2, what is r of x? R of x is almost x equal to 1/2. This comes from the numerator 2x minus 1. You copy 2x minus 1. And in other terms, you replace x by 1/2. So it's 1/2 plus 2. 2x minus 1 over 5/2 is is something like this, right? So this is a straight line with a positive slope. It's a straight line with a positive slope, okay? So that is a xy intercept and the behavior near x-intercept. And then let's look for the vertical asymptote. Vertical asymptote in the lowest terms, there's only one factor x plus 2. So the x equal to negative 2 is the unique vertical asymptote. And in order to find the horizontal asymptote, we need the division. So we divide 2x minus 1 by x plus 2. Okay, 2x over x is 2, so it's 2x plus 4, 5. So the r of x is equal to 2 plus negative 5 over x plus 2. And this implies y equal to 2 is the horizontal asymptote. Horizontal asymptote. And the graph of the function can never intersect the vertical asymptote for the rational function. And the graph of the function may intersect the horizontal asymptote. So you just let r of x equal to 2. R of x equal to the horizontal asymptote and try to solve for x. And r of x is this. So okay, so it's 2 equal to this. You cancel 2, 2, you get a 0 is equal to negative 5 over x plus 2. Unfortunately, this one has no solution. A rational function is 0 if and only if the numerator is 0, but the numerator here is negative 5. It can never be 0, so it has no solution. No solution means the graph does not intersect this horizontal asymptote. Okay. 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 Step 6. No, this is step 5. Yeah, this is step 5. Step 4 is about vertical asymptote. Step 5 is a horizontal asymptote. Horizontal or slant oblique asymptote. Okay, now let's talk about step 6. Step 6, you're going to put the x-intercept and the zeros of denominator in the number line. 1/2, 2, negative 2. Okay, so you have 1, 2, 3, 4. You have 4 regions. You may pick up negative 3 from this region and negative 1 here, 1 here, and 3 here. And you evaluate the function r of a negative 3. You go back to the original function, try to evaluate, or you can just go to where? Oh, the lowest determinant to evaluate. It works. You do the evaluation, you will get this is 7. R of a negative 1 is negative 3. R of a positive 1 is 1/3. R of a 3 is 1. And then you know this is above x-axis. This is below the x-axis. This is above x-axis. This one is below x-axis. Okay. Okay, so that's what we can get for for the relative positions of a graph with respect to the x-axis. Step 7. Step 7, we're going to study the behavior close to the asymptotes. Okay. And check that. Okay, so this part, this is above x-axis. It's below the x-axis. So we have one vertical asymptote. Where is vertical? Vertical asymptote, x equal to -2, is the vertical asymptote. Then on the left-hand side, you just, for example, pick up x equal to -2.1. It's left side. You evaluate this value. R of -2.1 is equal to 2 times. You use a lowest term here. This is the lowest term. 2 times -2.1 minus 1 over -2.1 plus 2. You check that this is a positive number. The numerator, let's do it. Let's continue. 2 times -2.1 is -4.2 minus 1. Here's -0.1. So negative is positive. Positive, it implies on the left-hand side, the graph approaches positive infinity. Okay? And right-hand side, we choose x equal to -1.9. Then we get r of -1.9 equal to 2 times -1.9 minus 1 over -1.9 plus 2. The numerator is -3.8 minus 1 over 0.1. This time the denominator is positive. Numerator is still negative, so it implies the graph approaches negative infinity. Okay? The graph is approaching negative infinity. Okay, now let's check. How do we sketch it? Well, there's a horizontal asymptote, but the horizontal asymptote is a little bit strange. Let's see. Well, not strange. Let's check it. One. Okay. Well, let's check. We will get it. We have -2, +2, 1/2. Then the vertical asymptote is x equal to -2. Where is the 0? X-intercept. X-intercept is 1/2. At 1/2, it is a straight line with a positive asymptote, with a positive slope. So it's like this. And y-intercept is negative 1/2. Y-intercept is negative 1/2. Okay, so that's what we have so far. Let's check. At this point, there's no solution. There's no definition. Where is the horizontal asymptote? Horizontal asymptote, y equal to 2. And we know that at -3, the value is 7. So -3 is here, it's 7, it's this place. And on the left-hand side, the left-hand side of -2, left-hand side -2, it approaches past infinity. So it has to go this way. And when x approaches -infinity, the graph will approach the horizontal asymptote, so it has to go this way, right? And it cannot cross the horizontal asymptote because we just say there's just verified that there's no solution. There's no solution. Just because this -3, it is 7, it's above the horizontal asymptote, so the whole graph on this piece will be above the horizontal asymptote. It cannot cross it. It's like a floor. The vertical asymptote is like a wall. Okay, and when x approaches vertical asymptote from the right side, it's -infinity, so it's this way. So you connect them, and here it will approach horizontal asymptote. This in this when x approaches past infinity, because from below, because it cannot cross the horizontal asymptote, right? So you see here, if you want more precise, you can evaluate the -1. Yes, where is the -1? -1 is -3, so it's this place. You just try to connect them with a smooth curve. With a smooth curve. And be careful, at 2, there's no solution. You put a circle here. At 2, there's no solution. And if you want to make it more precise, at 1, remember here, at 1 you have 1/3. So this value you just estimate like 1/3. This value you estimate it like -3. Okay, so those points are also useful when you try to plot the graph. If there's no evidence for you to shake the graph, you just use a straight, smooth curve to connect the information you have. Okay, don't shake the graph. You don't have reason, you do not do that. So this is the function, the graph of the function. So from this graph, we can see that the function, this is rational function, it is not in the standard of, it is not in the lowest term. It has the numerator and the denominator has some common factors. You have to cancel the common factor in order to get the lowest term, and then you can determine the vertical asymptote from the lowest term. And the x equal to 0, x equal to 2, no, negative, x equal to -2, it gives you the vertical asymptote. And x minus 2 is cancelled, but since x minus 2 is in the denominator, in the original denominator, so x cannot be equal to 2, so there's a hole. So that's what the remark says. The remark is on page 363. The zeros of the denominator of a rational function gave rise to either vertical asymptotes or holes in the graph. So either vertical asymptote or holes in the graph. In the example in the last videos, we only have the vertical asymptote because the rational function is in the lowest term, and this one is not in the lowest term. You cancel some terms. You cancel terms, you will generate a hole. Okay, so that's the complete characterization for the zeros of the denominator. We'll give two types of stuff. One is vertical asymptote, the other one is a hole. That's the geometric meaning of the zeros of the denominator. Right? Very good. Now let's see the next example. So find a rational function that might have the graph shown in the figure. Okay, so we're trying, here we have a rational function. We try to graph it, and here we have a graph. We try to find the function, or we try to construct a function. Okay, let me this is a okay 2. This is a -5. X equal to -5, vertical asymptote. X equal to 2, another vertical asymptote. This point is 2, -2, and goes to infinity, and this is -2 also. Goes to infinity. It's a 5. This is y equal to 2. Okay. Okay, let's study. How do we sketch it? How do we find the function? So first of all, there is a 0, and the graph crosses this. There's an x-intercept. The graph crosses x-intercept. There's a second x-intercept. The graph touches second x-intercept. So you will have here, it is x minus 5. X minus 5, it has odd degree, it crosses it. And this is x minus -2. But since it touches it, so it's squared. It's a square. And actually, this part, you need -x minus -2 squared. This one, it opens up. With negative sign, it opens down. Right? If without a negative sign, it's a x plus 2 squared. It should open up. But this time it opens down. Okay, so that this property guarantees that you have the two zeros. You have two zeros. And of course, here we don't know if you put cube or put fifth power. Here it can be squared, it can be fourth power, can be sixth power, all the even power will play the similar role. But we just want to construct a function with more or less graph like this, so we just pick up smallest number. Okay, and the denominator here, there's no zero, so you do not cancel terms. There is no zero, you don't cancel terms. And the denominator, zeros of denominator will give you the, it's a numerator. Numerator. And for denominator, for denominator, you have two vertical asymptote. So that you have x minus -5, x minus 2. This is the denominator. And let's check when x minus, okay, these two things just guarantee we have the denominator, but I don't know if they go to the positive infinity on the left, negative infinity on the right, negative infinity on the left, positive infinity on the right. I have no idea about this the direction, so let's check it. For x equal to negative, close to -5. No, let's just put x equal to -5. Left side. Left side, we choose x equal to -5.1. X equal to -5.1, and then let me see. It's this way. How do I, it's not this, it's this way. How do I guarantee you have a positive infinity, negative infinity? For x equal to -5, x minus -5 is x plus 5. X plus 5, you see here, when x is less than -5, the sum is negative. The sum is what is the meaning of that? Okay, I pause this video for a few minutes. Let me explain this process again. For the -5, for -5 on one side it approaches positive infinity, on the other side approaches negative infinity. It just means this x plus 5, this term has odd multiplicity. You see some graph like this, the x minus c has odd multiplicity. Okay, and if this one, it will have a positive on the right side, a negative on the left side. So you will put a negative sign in order to justify, in order to change it, a positive on the left side, a negative on the right side. Why I put a negative sign? Remember that 1 over x, you see it should be positive on the right side, negative infinity on the left side. If you put a negative sign, it will switch the order. So this negative x plus 5 will appear in the denominator. Okay? So you don't have to examine it. I mean, of course, if you examine it, you will get the same thing. And for x equal to 2, for x equal to 2, it approaches the same place. If you recall that 1 over x squared, you will notice that when you have this vertical asymptote, they approach to the same direction, then the multiplicity is even. So x minus 2 has an even multiplicity. We're going to put square. And because if it is 1 over x squared, they both approaches positive infinity. Now the graph approaches negative infinity. So you put a negative x minus 2 squared. Okay, so far we have what? We have a numerator. Where's numerator? Numerator is here. Negative x minus 5 x plus 2 squared. And denominator, you have a negative x plus 5 times negative x minus 2 squared. So cancel them, you get a negative x minus 5 x plus 2 x plus 5 x minus 2 squared. Okay, and the thing is that we have to really know that this one is this direction or flip it. We add a negative sign, so you just pick up one point, pick up one, for example, negative 2. For x equal to negative 2, close to it, let's check the values. Let's check. On x is negative 2, you keep this x plus 2 squared. You keep this, and whenever you have other factors, you replace x by negative 2. So you get negative 2 minus 5 over negative 2 plus 5 and negative 2 minus 2 squared. And this is what? X plus 2 squared. This is a negative 7. It's a positive 3 times this is a 4 squared. So it is equal to negative 48.7 x plus 2 squared. This is already a parabola opening down. This is already a parabola opening down. It has negative coefficient, so you don't need this negative sign. We originally put a negative sign because we see that it is a parabola opening down. We need a negative sign, so we artificially put a negative sign. And after you see here, you have this building block, that building block. You have a lot of building blocks. They interact each other. So after you figure out the complete stuff, you can just check what is the proper sign. Do you really need this negative sign or not? Or it's like the textbook. Textbook will ignore this negative sign from beginning. The textbook even didn't discuss the negative sign because this is really a coincidence. Normally, you should discuss the negative sign, see if you need to add additional negative sign or you don't add a negative sign. Okay, so this negative sign, you only just check one point. That's enough. You can check negative 2. You can also check 5. Okay, for example, with this negative 7 over 48, we don't need this negative sign. Okay, if you do not check negative 2, let's check 5. For x equal to 5, I put here x minus 5. And 5 plus 2 is a 7 squared. And 5 plus 5, 10. And 5 minus 2 is a 3 squared. So it's a 49 over 90 x minus 5. You see here, this one, it cross the line, the behavior near 5 is a straight segment. It has a positive slope. Here's a positive slope. So it's okay. So you don't need this extra negative sign. Okay, you can pick up either of the point. You can pick up a -2, 5, or you can pick up a -5 or +2. It doesn't matter. They will give you the consistent result. You don't need this negative sign. Okay, so now we put them together. We put all three building blocks together. So one more thing, the horizontal asymptote. Horizontal asymptote is 2. 2 means the numerator and denominator, they have the different coefficient. So here's the stuff. If we have a rational function as a n x n a n minus 1 x n minus 1 plus a0 and over the bn xn bn minus 1 xn minus 1 plus b0. The rational function, the numerator and the denominator have the same degree, then y equal to an over bn is the horizontal asymptote. You just check the ratio of the leading coefficient. Check the ratio of leading coefficient. Here, the ratio of the leading coefficient is 1. We don't have 2. So we multiply the numerator by 2. The answer is 2 x minus 5 x plus 2 squared over x plus 5 x minus 2 squared. This 2 comes from the final discussion. Okay, so this is one example. It's very bad because we didn't have enough exercise. We will have another one. Let's check. What did we do? We examined the zeros. We get x minus 5, x minus -2. And if it crosses the x-axis, we put 1. If the graph touches x-axis, we put 2. And then we study the vertical asymptote. Vertical asymptote, if on two sides the graph approach to the different direction, we put 1. The power is 1. Power is 1 here. If they approach to the same direction, the power we put 2. 2 is here. And then we put the building blocks together. For the simplicity, let's forget the negative sign. Here you don't need negative sign. Here let's ignore the negative sign. After you put all the building blocks together, you randomly pick up one point, either the x-intercept or the vertical asymptote. You pick up one point, you try to determine the behavior near it. Let's to match this direction. To match it. If it does not match the stuff, you put a negative sign. Okay, so that's the final step to justify the negative sign or positive sign. And then you check the horizontal asymptote. If it has a horizontal asymptote, you need to multiply top and bottom by a proper factor. Okay, horizontal asymptote is the ratio of the leading coefficient when they have the same degree. Okay, let's do another example. Uh, 46. This is x equal to -1, x equal to +1. And this is y equal to 0. Y equal to 0, that's our horizontal asymptote. Okay, there's only one x-intercept, so the numerator is x. 0. x-intercept is 0. So okay, 0 is the x-intercept. So the numerator contains x minus 0. It's just x term, and it cross the x-axis, so its a degree is odd. And you have two vertical asymptotes, x equal to -1 and x equal to 1 are vertical asymptote. And they both have different infinity. Here's positive, here's negative, positive, negative. So the denominator contains x minus 1, x minus -1. They both have degree, odd degree, because they have different direction. Okay, so that's everything. That's everything we have so far. We just studied the x-intercept. We studied the vertical asymptote. So we have the candidate x over x minus 1, x plus 1. Okay, so that's the current situation. And actually, if you examine it, the degree of the denominator is 2. The degree of the numerator is 1. So this is a proper rational function. For the proper rational function, y equal to 0 is the horizontal asymptote. So it also satisfies the horizontal asymptote. Just this is an example. It's a simple example. So you don't have to worry about the horizontal asymptote. Now my concern is that is this a positive function or negative function? Should I put a negative sign or not? Let's check. For x equal to 0. X equal to 0 comes from x. Let's check. So it is x over 0 minus 1 and 0 plus 1. It is negative x, right? 0 minus 1, negative 1. 0 plus 1, positive 1. Divided by 1. Negative x. Negative x is wrong. Negative x means it has negative slope. Here it has positive slope, right? It does not match this graph at this point, so you have to put, so r of x should be negative x, x minus 1, x plus 1. It should be like this. This one, actually, you can also pick up, for example, let's pick up x equal to -1. X equal to -1, if we check the left part, we require a positive infinity. Let's check. Let's choose x equal to -1.1. -1.1, let's examine it. The numerator is -1.1 over -1.1 minus 1, -1.1 plus 1. So it's -1.1 over here is -2.1 times -0.1. So you see here, negative, 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 it is equal to a negative number. But we need a positive infinity. So we have to add a negative sign. So this is another way, this is the case when you choose -1 as a testing point to check the negative sign. It doesn't matter, you can choose -1, +1, or you can choose 0. Finally, you have to put this negative sign. Let's see another one. This is a very difficult problem. Oops, sorry. My bad. So x equal to -1 is here. Y equal to 1. Graph looks like this. 1. It's a 3. Okay. Okay, let's check. Numerate the x-intercept. X-intercept, x minus 1, x minus 3. This is numerate. The graph both cross the x-axis, so they both have degree 1, odd power. Okay, that's everything. That's everything for the numerator. And the vertical asymptote. Vertical asymptote, x minus negative 1, x minus 2. You see here they both approach either positive infinity or negative infinity. They share the same direction, so they're both squared, denominator. And then let's let's put them together. So it's x minus 1, x minus 3, x plus 1 squared, x minus 2 squared. Then we have to check the direction, the sign. Is this proper or not, a correct direction or not? Either way, you can choose 1, 3, or negative 1, positive 2. This time, let's try to choose positive 2. X is equal to positive 2. We want to see the direction. Let's assume x is 2.1. 2.1, it should be negative infinity. You need a negative 0, negative number. So it's 2.1 minus 1, 2.1 minus 3, and 2.1 plus 1 squared, 2.1 minus 2 squared. So it's 1.1 times negative 0.9. It's 3.1 squared, 0.1 squared. Okay, positive, negative, positive, positive is negative. Good, it fits the property. Okay, so it fits the property. You don't have to put a negative sign. You do not have to put a negative sign because it is negative. We're almost done, except this horizontal asymptote. This is a proper rational function. Its horizontal asymptote is 0. Even you multiply it by 2, by 3, by whatever number, it is still 0. Because a proper function, you multiply the top numerator by whatever number, it does not change the properness. But you have horizontal asymptote 1. How do I do it? Add 1. You kind of lift it up 1 unit. So r of x could be x minus 1, x minus 3, x plus 1 squared, x minus 2 squared, and plus 1. This plus 1 is used to match this horizontal asymptote y equal to 1. Okay, so this type of problem is like the reverse process for us to understand the steps of graphing problems. Okay, that's it. That's this section. We finished this section. Do the exercise. Make sure you understand it. I select those two from the. This is a 47. That one was a 46. This is a 46. This is a 47. There's still 45 and 48. Try to do them and try to understand the reason behind the selections. Okay, we'll stop the video here. Thank you.